coming up. How about that?
Oh, there you are. Yep.
Wow. I see what you did there.
Adjust this again. Okay, so this is my next physics class, so if you want to go ahead and get started, you're welcome to.
Okay. So my name is Jake Anderson, and I'm an associate. I'm a research associate here at Fermilab outside of Chicago in Illinois. I work on the CMS detector, which is at the LHC at CERN in Switzerland, and I have been working on that experiment for the last 3 years now. Before that, I was a graduate student. I was at the University of Maryland working on my PhD, where I worked on the bar experiment, which was at the SLAC accelerator in California. So just give a little background on myself. And so I've been at CMS, I've been involved with searches for the Higgs boson as well as other exotic particles and other things in the standard model. So your teacher asked if I give a brief overview of the standard model, also talk about why the Higgs boson is so important. It gets called the God particle sometimes. And then I'll say a little bit about those different things. So just to start things out, on slide number 2, on the second slide that I sent, just that talks about, what is science, and just my view on it is that science is all about asking questions. You gotta ask how, you gotta ask what, you gotta ask why, and if you really want to learn anything, you gotta ask questions. So if there's something I say that just doesn't make any sense, you can ask me a question, and maybe I'll ask some questions too. And so going on to the next one, in particle physics, what we're really interested in are building blocks. What is everything made of? What we're interested in is reductionism, basically. What is the most fundamental thing in the universe? What is it all made up of? And what about energy? What about the forces that push things around, that pull things in? They have to interact in some way. If we have theories but we have no interactions, those are really boring because everything just sits there and doesn't do anything. Okay, so really at its core, this physics is trying to answer these questions. What is everything made of? What are the basic building blocks? And how do they interact with each other? Okay, so in chemistry, you learn about atoms in particular, and for chemistry, that's really the most important thing, and that's as far as you need to go. But physicists a lot of times want to break things down even farther. So on slide number 4, you've got the atom, but you've also got it broken down even farther. You learn that the atom is made up of protons, neutrons, and electrons, and the protons and neutrons live in the nucleus. But are those the most fundamental things that you have? Well, in the 50s, they discovered that, in fact, you could break the protons apart. The protons and neutrons can actually be broken apart, and they called those things that they were made out of quarks. Nobody has been successful in breaking apart the electron, and so far as we know, the electron is a fundamental particle, as are the quarks. And so on slide number 5, I have a table. There are these 12 particles. These are the 12 particles which are fundamental building blocks of matter that we know of. They're in 2 different groups, and then each group has 3 different families, so you can see these 12. There are the leptons. All of them are spin 1/2. The leptons, the electron that you know about, and it has a neutrino that goes with it. But there's also the muon and the tau with their own neutrinos. And then there are the quarks. And so the up and down, which make up the proton and neutron, but they're also the charm quark, the strange quark, top and the bottom quark. And so those are the quarks. The thing that distinguishes the two, the leptons and the quarks, is that the quarks participate in the nuclear force. So the strong nuclear force, which is what binds the protons together, binds the nucleus together, and the leptons do not feel that force at all. They are completely oblivious to that. And so one other thing that's very interesting that scientists particularly find very interesting is that there happen to be 6 leptons and 6 quarks. And so there are theories which try to predict why there are the same number of quarks as there are leptons. But so far none of those theories have been experimentally verified, but they do exist. But it's certainly a striking coincidence that there are 6 of each. Okay? And so as far as we know, these 12 particles are the fundamental particles that make up everything that exists. Now there are problems with this there's, for example, you may have heard of dark matter. You can see here that there's no dark matter particle anywhere to be seen, and that's one of the problems with the Standard Model. That's one of the reasons that people think the Standard Model might be broken. There are also, all of these particles have an antimatter partner. So every particle has an antiparticle which corresponds to it, which means that there's technically not 12 but 24 fundamental particles, but that's just a technicality. So now we've got all the particles, we've got to make them do something. So if we go to the next page, we'll talk about forces. So I already talked a little bit about these forces. So for example, the strong force, which is on the right side, that's the gluon it's called. And so that is what binds together the nucleus, that binds together the quarks into a proton and into a neutron. All of these things is extremely strong force, but it's also a very short range force. And in general, and so that's the gluon, and that's what we call the color force. There's also the electroweak force on the left side, and there are 4 bosons which carry the electroweak force. There's the photon, which is light, the electromagnetic photon, okay, which is very common, everybody's experienced that one. But there are also the W plus, there are 2 W bosons, the positive and negative one, and then there's a Z boson, which is neutral. And one thing that's very interesting about those bosons is that they are heavy. So these are force carriers which are very heavy. You look at their mass is 80 GeV, or 90 GeV, 91 GeV, and when you compare that to a proton's mass is 2 GeV. And so these are 40 times heavier than a proton. And a proton is the heaviest thing in the nucleus. So these are very heavy. These are as heavy as the entire nucleus of what is, I can't remember what's 40 now, but I think it's carbon or something like that. Is silicon or something like that. It's very heavy. So these are very heavy particles, but they're fundamental. Okay, these carry the forces. So remember that the strong force only applies to the quarks. The electroweak force applies to all the particles. Okay, and so one of the things that's very interesting is what makes these particles so heavy. And so if we go to the next slide, the Standard Model is not perfect by any means, but it is wildly successful. Okay, there are very few measurements that exist in all of physics which contradict the Standard Model. Okay, and the 4 major ones are listed right here. One is the accelerating universe, okay, that when we look out into space, it looks like everything is accelerating. The second one is why there is no antimatter, right? We talked about the antiparticles, and when we look out into space, we look at everything is made of protons, regular protons. Where are all the antiprotons that go along with those? Where are all the anti-electrons? Where is all the antimatter? That's one of the things that we struggle with, is that there is no antimatter in the universe, relatively speaking. Another one is dark matter. We talked a little bit about that. That of all of the matter in the universe, roughly 80% of it is dark matter. And so the Standard Model has no particle for 80% of the universe, which is kind of a problem. And then the last one is the origin of mass. And so we don't understand the origin of mass, but the Standard Model does have something to say about this. It has the Higgs boson, and we'll talk about that in just a moment. And so that is in the Standard Model what the origin of mass is. Now we haven't found the Higgs boson yet, but to say that the Standard Model doesn't cover it is kind of misleading, I would say. But the Standard Model does predict that there could be a Higgs boson, but there could be more than one. The Standard Model only has one. There could be more than one, or there could be none at all, which would be a problem for the Standard Model. So if we go to the next slide, why is the Higgs boson so important? So the Higgs boson is predicted by the Standard Model, and it's very important because on the symmetry basis. So symmetry plays a very important role in all of physics and a lot of pretty much all of science as well. So the one that's most interesting and that maybe you guys could understand and that applies particularly is when you talk about, for example, in physics, an important thing is conservation of momentum. And I'm sure you guys have worked with conservation of momentum. You know that that's one of the laws of physics and stuff like that. The reason that momentum is conserved fundamentally comes from the symmetry. And the symmetry that provides conservation of momentum is the fact that the laws of nature don't change. I'm here at Fermilab, and I study physics. You guys are in New York, you guys are studying physics. The fact that we're studying the same physics is because the laws of nature don't depend on where I'm sitting. When I go to Switzerland and study physics, I'm studying the same laws of nature. If I go to the moon and I study physics, I'm studying the same laws of nature. And so because physics is the same no matter where your location is, that symmetry of translation, the symmetry of space, is the reason that there's conservation of momentum. And so it's a very powerful, these symmetries are very powerful in determining the laws of nature. And so in the standard model, there's a symmetry which tells how the W, the Z, and the photon interact with everything. And if the W, the Z, or the photon have mass, that symmetry doesn't exist. That symmetry is broken. And so if you don't have any interactions, you have a very boring model because the W, the Z, and the photon do nothing. They just sit there, and all the particles just sit there and do nothing. And nobody wants to study a model like that. Nobody wants to study the standard model because it doesn't do anything. So you can get around this problem by what is called spontaneously broken symmetry. So the Higgs mechanism spontaneously breaks the symmetry. The way that you can think of spontaneously broken symmetry is if you take your pencil and you balance it on the point of the pencil, you have a radial symmetry. The pencil is perfectly, it doesn't point in any direction. It doesn't point north, doesn't point south, doesn't point east, doesn't point west. Okay, it is perfectly symmetric. But as soon as you let go of that pencil, it is not going to stay in that symmetric configuration for more than a second. It's going to fall over, and the symmetry is broken. Even though you started from a perfectly symmetric state, it's broken, and the pencil is going to point in a direction. Now, you may not be able to predict what direction that is, but it is going to point in a direction that's not going to be symmetric anymore. And so that's the same thing with the Higgs mechanism. So we can start with a symmetric case, with a symmetric situation, and it's broken. And when it's broken, the W and the Z, like we saw on the previous slide, get masses, and they become very heavy. Okay, the photon does not become heavy. It's protected by a second symmetry, its mass is. But so in a matter of speaking, if you didn't have the Higgs, you wouldn't have any interactions. The standard model would be the most boring standard model you've ever come up with because nothing did anything. It just sat there. And so it wouldn't be very interesting. So that's why the Higgs particle gets called the God particle. It gets called lots of different things. But it's extremely important to the standard model because without the Higgs boson, you'd have no interactions. The name God particle came from Leon Lederman. It's kind of an interesting story, so you can ask me about that at the end. So if we go to slide number 9, this is, how do we go about looking for the Higgs boson? So I just want to say that, the Higgs boson is basically the last unobserved fundamental particle in the standard model. So if you think of the standard model like a jigsaw puzzle, there's only one piece missing. But if you have every piece in a jigsaw puzzle except for one, you pretty much know almost everything about that piece. And that's the way it is with the Higgs particle. We know almost everything about it, mass is, but we know almost everything else about it. Okay, because it is the last. Once you've narrowed down everything else, you pretty much know what that last piece is going to look like. So how do we go about looking for it? So I've put a plot here, which is this is the Higgs to gamma to 2 photons. So this is the invariant mass. So we plot the mass of these things, and you can see that it has kind of an exponential decay. And what you're looking for not a smooth exponential decay. You're looking for a bump. So you start at 90 JeV, and you have a lot of events there, and they decay away. By the time you get to 180 JeV, there's not so many events. But you're looking for not just a smooth decay function. you're looking for a bump. And so they've drawn in here the Higgs. If the Higgs had a mass of 120 JeV, you would see a bump that looks something like the red bump, except for they've blown it up by a magnification factor of 5. Okay, so that magnification factor of 5 is what lets you kind of see it better by eye, if it were 120. And then I went ahead and I moved that red bump up a little bit so you can see what it looked like, if it was on top of the background. Okay, so you can kind of see that. Now, in all of the searches so far, we haven't found definitively where the Higgs boson lives, what its mass is, anything like that. Our best guess right now is actually that it's not 120 JeV, it's 125. So if you look just to the right of that red bump, if you look at those points, you can see that there are a couple of points which are kind of peeking up above the background line. And those couple of points are our best estimate of where the Higgs boson lives. And so if you look at that, you say, I don't know, that doesn't really look like a bump to me. And you'd be right, because there is not a particularly strong bump, and we can't say definitively yet if it is just a statistical fluctuation, if we just have some noise, some extra noise or something like that, or if there really is a bump in that position. And so that's going to take some more data, and that's why we're running again for the next few years and stuff like that, is to really define where that bump is. So that's kind of, and so then once we have a Higgs boson, that completes the standard model. And if you go to slide number 10 that I have, that's kind of the next frontier. The LHC is really built as a discovery machine, and it's got more energy than any accelerator has ever had. It collects more data than any accelerator ever has, and it collects it faster than any accelerator ever has. And so this gives us the opportunity to search for that Higgs boson, which is the last particle. It gives us an opportunity to search for new particles, which are not predicted by the standard model. Remember, we're missing the dark matter particle. Maybe we could find that at the LHC. We are missing lots of different things. There are lots of things. The standard model also has other problems, which I didn't talk about, where it kind of breaks down at a certain level. Once you get so much energy, the standard model freaks out and it goes crazy. Okay, so there must be something that makes it not go crazy. So we're looking for those particles that could, make it not go crazy. And so in the coming decade, next 10 years, we'll probably, many of those particles, back on the first couple of pages where I showed you those 12 particles, we may add new particles to those. Or we may find out that those particles are not in fact fundamental. We may say, well, those particles are actually made of smaller particles, and we'll be reducing things down farther. And but all of that is going to be contingent on what the LHC finds. And the LHC is really, it is built to discover these things and to really break the standard model as well as confirm it. So the last page is just a website that I put on there, the Particle Adventure. That one's put out by the Department of Energy and the National Science Foundation. It's kind of fun. It has a lot of interesting things about particle physics and how accelerators work and how we search for particles and stuff like that. So if you have time, you can go try that out. It's a lot of fun sometimes. So that's pretty much what I have. You guys want to ask some questions? I'm willing to answer questions on anything, science, university, the NCAA tournament, what the weather, why we have this crazy weather, I don't know. So if you have any questions, go right ahead.
You see him okay?
Yeah, I can see everybody.
I know you mentioned on slide 5 that each of the 12 particles has an antiparticle too. So
That's right.
Does the Higgs boson have an antiparticle?
The Higgs boson does not have an antiparticle. It is its own antiparticle, actually. It does have an antiparticle that same way. So it is possible for a particle to be its own antiparticle. For example, the photon is actually its own antiparticle. So that's how it works. But yes, every particle has its own antiparticle, but some of them happen to be itself.
And if you're looking for the Higgs boson right now, that's like the unknown particle. Before you, were there any other unknown particles before this?
So the last unknown particle was the top quark. The top quark was discovered at Fermilab in 1995, I believe it was. If I remember correctly, I was in high school then taking physics when the top quark was discovered in 1995. And it was, so they had a spot for it in the standard model. There was a placeholder left. They said, we think that there's a top quark, and we think that it should be around here. And it was the temperature here at Fermilab, which actually discovered the top quark in 1995. So there have been other missing pieces. The standard model itself was not really put together the way it is now until the 1970s late, and most of the particles had it discovered. The top and bottom and stuff like that were not discovered yet, and so those were kind of the ones that were predicted by the standard model. Before that, they had other models that only had the particles that they knew about, but finally with the electrical and the circulating and stuff like that, with the coming of the Higgs mechanism, they put them all together. And it predicted the quark, and then they found the top quark. It predicts the Higgs boson. So far, we haven't found one. So if we don't find one, that's really interesting also, because that means the standard model is wrong. And we're going to have to figure something else out.
Thank you.
Yep.
You guys, Mike? You guys got questions? I'm gonna follow up with what he was just saying. Can you kind of explain, what this whole deal is? We're still on this slide 5. What it means by spin, and then what antimatter, how that is referenced to the spin, how they make antimatter.
Okay, so spin is a fundamental property of each particle. And you can think of it if you consider these particles to be little balls, okay, like billiard balls, then you can consider it that they spin, okay? They're not, in fact, like billiard balls. As far as we can tell, all of these particles are point particles. They have no radius. The radius is 0. But they have a magnetic moment. And because they have a magnetic moment, it's as if they are little spinning charged particles. And so because of this magnetic moment, we label that property spin. And antiparticles are just like their regular particles, okay, except for that they have their charges backwards, for example. So the electron, they have, a lot of their things are backwards. Anything that has a sign, if they have a sign, if they have a property which has a sign, it can be either positive or negative, then the particle will have a positive sign and the antiparticle will have a negative sign. So the easiest one, for example, is charge. So if you take the electron has a negative charge, right? So if you go to an anti-electron, which is called a positron, the positron has a positive charge. Now, if you take something like mass, so mass, there's no such thing as negative mass, right? Or at least not that we know of. So if you measure the positron's mass is exactly identical to the electron's mass. So they are twins, except that the one has a positive charge, one has a negative charge. The same way, because spin is not negative, so spin is also same for both of them. And so just on that grounds, you can say, so I told you that some particles are actually their own antiparticle. You can rule out anything that is charged cannot be its own antiparticle. So the photon doesn't have an electric charge, it's neutral. And so it's possible that it could be its antiparticle. The quarks, you can see that all the quarks have an electric charge, a non-zero electric charge. None of them are neutral. So they cannot be their own antiparticle. They're all anti-up, anti-down, anti-charm. Everything has its own separate antiparticle. The neutrinos, we believe that they have an antiparticle which is separate, but that hasn't been actually completely ruled out yet. And there are some people who believe that the neutrino is a Majorana fermion, and that means that it would be its own antiparticle. But so far, nobody can tell. So right now, as far as we can tell, there is actually a separate antineutrinos as opposed to neutrinos. But that's subject to change.
Nick, you have a question?
Yes, actually I do.
So, for quarks, the up and down quarks are found in protons and neutrons. Where would we find the other 4 quarks?
So the other 4 quarks are heavy. You can see that they're much heavier than the charm strange top and bottom are much heavier. They're not stable. So even though they are fundamental, even fundamental particles can decay into lighter particles. And so the charm, the strange, the top and the bottom, they all decay into lighter quarks. And so eventually they all decay down to the up and down quark. And so that's what happens to them. They don't exist in nature because they're too short-lived. They have lifetimes which are very short. It's a couple of nanoseconds is all, sometimes even shorter, picoseconds or even less. So the top quark basically has almost a zero lifetime. It lives, less than a picosecond, so before it decays into a lighter quarks. So they do not exist outside the particle accelerators. But they also existed during the Big Bang.
Jake, would you be able to explain to this class, like you did the other class, about how particle accelerators first determine how they find quarks, and then how they determine like the charm quark at Stanford Linear Collider?
Right, so the charm quark was certainly one of the most exciting ones. And so when you go looking for particles, what you're looking for, just like I showed with the Higgs one, you're looking for a bump on the background, on a smooth. And so the charm quark was an extremely exciting one, because that one, so I sit in my office, write computer programs to sift through the data and do lots of statistical analysis. The charm quark was not like that. The charm quark, they discovered it sitting in the control room. And so they're playing with the knobs on the accelerator, turning the energy up and down, and they find that as they go to a certain energy, the accelerator goes crazy and it starts producing tons and tons of particles. And if you turn the knob a little bit to the left and the energy goes down a little bit, you get very few particles. If you turn it a little bit to the right and you go past that energy, you go to a little higher energy, you don't get very many particles. If you turn to just this this right energy, which happens to be, you can see that the charm quark is 1.3 GeV. If you turn it to basically twice that, to just a little bit over to almost 3 GeV, then you find that your accelerator goes crazy and you start producing all of these particles. And they're just like, that is a resonance. And so what they have is they know that when they tune it past other places where they know particles already exist, then the same thing happens. And so they said, we found a brand new particle. We know, but we don't even have to do any analysis. We have found a brand new particle. And so right there in the control room, they started writing a paper. And it happens that, only a couple of days later, they sent that paper to one of the most prestigious publications, one of the most prestigious journals. And that was how they discovered the charm quark. It was a very exciting discovery out in SLAC that really rewrote all the rules. Because up until then, there were only 3 quarks. There was the up quark, the down quark, and the strange quark. And they had a separate symmetry called isospin that included those 3 quarks, and that was it. They didn't know that there were any other quarks. They had no prediction for other quarks because they only had a different symmetry, which only admitted 3. And so when they discovered that one, it was very exciting. And so they really, went bonkers about that because they found this peak. And so that's really what you're looking for, is you're looking for this peak. You're looking for a bump where you don't expect one. So, was there something else I was supposed to explain?
No, just the whole story, just like you told it again. They didn't. This is a different class, so they didn't get to hear that. And I think, Nick, does that help you kind of how they find these top and bottom, and then the rest of the quarks by using the particle accelerators? Now, something I want to point out with these guys, they're not too familiar with this. They know what an electron volt is, and the GeV is a giga electron volts. But what you'd use with a particle accelerator is when you accelerate these particles, you add all this energy, and you accelerate them to close to the speed of light, right?
That's right.
And in the mass that's on here says GeV divided by c squared, and you're determining the mass because you accelerate them with such energy at the speed of light or close to the speed of light. You're using Einstein's equation E equals mc squared to determine what the mass of these particles are when you find them with the detector.
That's right. Right. So we measure mass in electron volts per c squared because it makes Einstein's equation. We don't have to do any math anymore. If we want to know how much energy there is, we just move the c squared to the other side, and we have E equals mc squared. right? So we just keep the c squared. We never actually put in the value for the speed of light. We just measure everything in terms of GeV or MeV or whatever, in terms of electron volts, because it makes the math a lot easier. C is, for particle physicists, the speed of light is 1, so you just ignore it. You can multiply by 1 all you want, you can divide by 1 all you want, it makes the math easy. So that's why we measure our masses in GeV, and that it is, the E equals mc squared. So we give these we accelerate things, so up to the LHC is protons. We accelerate these protons to close to the speed of light. And then we have all of that energy, all that kinetic energy, because they're moving so fast. You can convert that energy into something heavy, because E equals mc squared. And so once you've got that energy, you can produce something massive. So when you're talking about an electron accelerator, you accelerate these electrons. If you accelerate the electrons to 3 GeV, you can produce 2 charm quarks, because you can then if you take 2 charm quarks, actually charm and anti-charm, but they both have the same mass of 1.3, and so 1.3 times 2 is essentially 3. We're going to round it off to 3. And so you just take the c squared, and that works out really easy. If you have 3 GeV in your particle beam, then you can produce these charm quarks. And so it's all just E equals mc squared, and to keep the math easy, we just measure everything in terms of GeV, in terms of electron volts. That's right. So one thing is that the more energy you have, the heavier things you can produce. That's why the top quark, you can see how heavy the top quark is, 173 GeV. And that one was only discovered in 1995 with the tevatron, because until then there was no accelerator that had that much energy to be able to produce something that heavy. And so now we're at the LHC. The LHC has 7 TeV. So it's 7 tera-electron volts, which is even heavier. And so a lot of people are hoping to produce new particles which are even heavier than the top quark. So far we haven't seen any of those particles, but that's what everybody hopes. Eventually the LHC is going to go to 13 or 14 TeV, which makes it so we can produce things which are even heavier. So a lot of people are really hopeful to see a lot of heavy things, but so far not yet.
How is it that with the Large Hadron Collider, they say they can understand the environment when the Big Bang? How does that correlate between having particles accelerated and smashed, and then having the Big Bang? I don't know the scenario, I guess.
So the parallel is that when the Big Bang happened, all of the mass, all of the energy was that it had just this tremendous density and temperature. And what happens is when you collide these protons together in the LHC, for just a moment, you have the energy and mass density that is just like when the Big Bang, just like some number of femtoseconds after the Big Bang, some small number of femtoseconds after the Big Bang. And so that's why they call it, some people have called it the Big Bang machine and stuff like that, is because it recreates conditions that existed very shortly after the Big Bang. And where the energy density was so large and the number of particles you had in such a small area was so huge that, and then that all expands out just like the Big Bang did, and creates the universe. So when it expands out, we form these new particles at the charm and top and bottom, these particles which don't exist now because our universe is so spread out and is cooled down. Everything has decayed down to the ground stage, to the lightest ones. And so now but in the accelerator, we can produce things that were produced in the Big Bang. So these heavy quarks, even though they don't exist anymore in nature really, they did exist in the Big Bang. And any time that you have a large acceleration, for example, near black holes or supernovae or something like that, where you can get particles really accelerated because they have a lot of energy, you can still produce these particles.
Well, thank you very much, Jake. The bell actually rang. Could everyone please give a round of applause? Thank you very much for giving us that light. Thank you.
Yeah, no problem.
All right, have a good one.
You too.